All right, so let's keep on looking at all these equations. So I decided not to talk about this equation. This equation is boring. So basically, this important message I put here about this over-reduction or overfitting issue, because it happens many times. A lot of work. So if you get a reduced model, or sometimes if you want to compile or tune a detailed model against the experimental data, you will face similar problems. Okay. So first of all, the tuning, in terms of tuning, we do have a model. Sometimes you get a large model, larger than necessary. Sometimes you get a smaller model. You get a one-step, two-step model. So for these two scenarios, you get a different type of problems to deal with. Okay. For small models, the issue is probably simpler. Let's see if you get a very complicated detailed model, it can give you some fine structures. It's like this kind of structures to predict. All right. But somehow you can only allow for 5 species. Let's say people ask you for 5 species reduced model. You can only get one reaction to tune, right? One step. So 3 parameters at most. So what happened? What did I? My hand touched something. Let me do it again. So you get this fine structure. So you want your reduced model to, or one-step model to do a good job everywhere, right? But the thing is, you get one step. Let's say you get this like this. A simple model can give you simple structures, right? There's no way you can just, how you massage it, it just cannot strike through everything. So what you can do is you can select a few targets. You see if I can I just drag this guy. My new toy is, well, so see, let's see if you select this point to be of interest. I want to match this point. What you can do, probably the best is what you can do is to do something like this, right? See, if this is a point for a tuning, for example, a certain flame speed or a certain ignition delay, that's pretty much the best you can do. If you're lucky, you get something else works well. You can find this point which works well. If you show this good agreement somewhere in your paper, it looks very impressive, right? Okay, but if you keep on digging, you will always find bad places. Somewhere the agreement is very bad or even totally wrong. Okay, so if you have the one-step reduced model or a few steps reduced model or a very simple whatever model, you try to give people to use. So don't just show people these points which work well. It works well here, works well there. You tell them where it doesn't work, or at least give them the range. Within the range, it works reasonably well, because that's all the information they need to have the idea where you can apply this model for, where you cannot apply this model for. So that's probably the only requirement if you want to use a very simple reduced model. So, so if somebody asks you for a 5 species model, you give it to him, because this one can predict flame speed and 1 ATM phase equal to 1. That's it. If you want to use it for anything else, you are on your own risk. Okay. So I guess engine people probably don't like it. They ask me for a one-step reduced model. They hope to get something work everywhere. I just couldn't do it. Okay. So 30, 40 years ago we couldn't. Right now we still couldn't. It's a simple math. You just cannot do it. So just be honest with what this model can do. That's all for simple model. And the story is rather straightforward, but it's getting a lot more complicated if you get a complicated model to tune against a few parameters. That will give you a lot of problem, because actually that can affect more people than model reduction. Because if you compile a detailed mechanism, you get 1,000 or 10,000 reactions to tune, right? So which one do you tune? To give you a simple example, let's see you only get 2 parameters to tune. Okay, 2 knobs. You can tune these knobs this way or that way. Try to make something look good. For example, you see this level goes up and down. If you turn this one, it go up. If you turn this down, it go up slowly. So one knob is sensitive. This is sensitive. This is non-sensitive, suppose. How would you tune these knobs to match this point? You try to turn the lower fanfare. It doesn't work that well. So how about change it? Oh, the upper one worked better, right? So typically people tend to tune the upper one. Actually, this makes a lot of sense because if this parameter is wrong, you can't possibly get any good agreement with the experiment. So obviously you tune the sensitive ones. But what happened to the slow ones? You already tuned it. You turned several rounds, nothing happened. So what would you do with it? The chances that you will leave it there. Don't care what happens. But then when you use this knob, this panel, whatever device, try to predict something else. Another quantity is sensitive to this guy. What do you think will happen to this? This is what happens if you use a complicated model. You use a tuning, try to fit something. Typically, if you fit against the experiments, the number of experiment data is very limited, but you get a much larger number of parameters you could possibly tune. Some are sensitive, some are not sensitive. Those non-sensitive ones, you can easily mess them up. But if you use this tuned model for something else, if the sensitivity pattern is different, you will have trouble. So that's the case. So therefore, if you want to show how the tuned model, if you tune a detailed model, if you want to show people how this tuned detailed model works, it doesn't tell you anything, any useful information, if you only show how it works for this guy. Because it's supposed to work for this guy. You can always tune. You have numerous ways to tune to make this point look good. So in optimization study, people realize this already. If you have a complicated model, you can always tune it to match some simple target. But then if you use for something else, it's messed up. How to avoid this issue? It's kind of difficult. First of all, you try not to tune too much, okay? If you want to tune something, try to tune a simple model. You probably prefer to tune even the over-reduced model rather than a more complicated model. So if you have to tune a larger model, you try to include as many targets as possible. If you have experiment data, you tune against experiment data. If you don't have experiment data, if you have other detailed model to tune against, put all of them together to tune. So the more parameters you have to do the tuning, the better chance you have to avoid overfitting. Okay. Then another standard approach is you choose your target parameter to fit against. Don't always use everything you have. You choose only a subset for tuning. Right? That's the so-called the target set. But you do some tuning at the same time. You check how good this tuned model works against those targets not included. That's called the test sets. If you see the error for target sets goes down quickly, but then the error doesn't decrease anymore for the test set, you don't want to further tune it because it doesn't make any sense any further. So this approach can quite effectively avoid overfitting issue. So you tune against something, but you see how it works for something not included. So because that one tells you whether the model actually in ballpark is getting better or not. Yeah, and when you write a paper, try not to include this one. You try to get some other parameters showing the so-called validation set. You show how it works actually for irrelevant problem not included here in the optimization process. This is basically the standard approach used in the optimization society. So if you do neural network fitting, this is the standard approach. So people have realized this issue. But somehow in our society, we just didn't care too much yet about this procedure. Easily you can find papers published. Say, we tune the parameters to fit this target, this target, this target, and then they show in the paper these targets give you good agreement. Now you see the problem, right? So try not to do this if you have to tune large models. All right, so let's just that's all what I want to say about this tuning issue. So let's go back to the next topic. The next topic is I have two more topics to go through. So this one is something I want to mention because in the beginning, yesterday, I mentioned if you want to improve your solvers, so Jacobian is an important part, right? You have to deal with it with analytic Jacobian, also with sparse Jacobian operation. If you deal with Jacobian right, then diffusion matrix evaluation pops up. It gives you chi-square computational cost. Can we possibly get rid of this cost, or even reduce, or at least reduce it? So this is something we did before, and also recently try to just get rid of the cost almost from diffusion coefficient evaluation. So here is basically the scenario. So we compared how much diffusion evaluation cost, how much chemistry rate evaluation cost. You know, for small models, chemistry takes more time to evaluate the reaction rates, right? But for larger mechanism with you know, diffusion can take more time to evaluate than chemical reaction rates. For particularly if you get several hundred thousand species, because this is a quadratic function. This is a linear function. It crosses somewhere. So in the past, people have been using all different ideas to simplify diffusion model. So probably the earliest one is to use the so-called Lewis number model. We just assume a Lewis number is one or point something in turbulent flames. In turbulent CFD simulation, you see a lot of people using Lewis number approach. If you specify a single Lewis number, you will see a lot of cases you can get very, very bad results. Bad result, it means that doesn't give you 20% error, 10%. The error can be a factor of 2, sometimes even a factor of a few. Even the flame speed can be totally wrong. Okay, so this just shows if you assume a single Lewis number, if it's not right, how much you can mess up the flame speed. So that error is much larger compared. This is a counterflow extinction. This is a 1D flame speed. You can this one is the error is about 1 order of magnitude. Okay, this is almost a factor of 2. Let's say 20-30%. Oh no, let's say 20-30% error in flame speed. So, but if you look at flame speed, if you get 30% error in flame speed, you consider how much reduction in kinetics you need to do to get such an error. So flame speed is not very sensitive to a lot of reaction pathways. So that means if you reduce the chemistry to very small sizes, sometimes you can still make flame speed roughly correct. Okay, but if you mess up diffusion, easily the flame speed just goes wrong. So we do need to be quantitative in reduced models, particularly if you want to run, let's say, DNS with good chemistry, with good diffusion model. So how can we do with this? Let's just skip this one. Let's target our mixture average diffusion. Mixture average diffusion, you get this formula, right? It's diffusion flux equal to, for each species, there is a average diffusivity times the gradient of the concentration. So the D is evaluated using this formula. So basically, this is the minor, this is the minor. If you look at this basically is average diffusivity with a weighting factor of the concentration of the species. If you get a larger concentration for the species, it plays more role in this weighting. So it's a concentration weighted average for the binary diffusivity. So it makes a lot of sense, right? So how can we evaluate this D? You need to compute a whole big matrix, a square matrix of binary diffusion matrix. The binary diffusion matrix, if you look at the combustion books, you get a long integrals, very complicated. So you cannot possibly integrate all those formulas on the fly during your simulation. So people do tabulation of it using polynomials. So use polynomials inside an exponential function. So every time you compute one binary diffusion coefficient, you need to do a polynomial fitting and also just evaluate a polynomial and also do an exponential function evaluation. So that's why the exponential function evaluation makes each entry evaluation just like a rate evaluation, Arrhenius term. Because exponential functions takes most time in the computational process. Okay, so the idea here to reduce the cost is if you get an n by n diffusion matrix, we know the diffusivities are strongly affected by several parameters. For example, first of all, molecular weight. Heavier molecules diffuse slow because its molecules move slow, right? At the same temperature, large guys move slow, small guys move fast. So therefore, if two species have similar molecular weight, they tend to move at similar speed. And you know the similar speed give you similar collision patterns, their diffusion coefficient tends to be similar, right? Secondly, if the two molecules look structure is similar, they're all spheres or they look similar. So their collision cross-section areas look similar. So those parameters, if they are all similar to each other, in terms of collision, the two molecules are just the same, right? So why don't we just treat them as a single group? So you find all the similar groups, similar species, group them together. You just need to treat a few groups. So it turned out this idea works quite well. So this figure is to demonstrate for a lot of species. For example, species O and OH, they have similar molecular weight. Their collision everything just looks similar to each other, with very minor. And this is DIG. So the diffusivity O and OH with respect to every other species. For example, H to this major species. Okay, so this line are the D for O, and the symbols are the D for OH. You can see they are almost identical. So therefore, O and OH, their diffusivity are the same in other people's eyes. So we just treat them as the same group. And then we just need to find who can be grouped together, right? It turned out this is an interesting discrete mathematical problem. What we do is let me just go over this first. This is the criteria we can see who are similar to each other. For example, if we get a species I, species G, so what we do is we can evaluate their diffusivity at whatever temperature. Okay, we look at the ratio. We take the log. If they are close, you know, this log value tells you roughly the relative difference between the two species. You know, log if x divided by y, if they're close, log give you almost 0. The non-zero part tells you the relative difference. So this tells you the relative error between these two diffusivity. Then you evaluate this error for every other species and all the temperature range. This ratio is only a function of temperature. So you just need to evaluate from 3,000 Kelvin to 300 Kelvin, cover all the possible temperature range, and you check all the other species. If the worst case error is smaller than the threshold, let's see 10%, 5%, then you treat them as the same, one group, okay? Then you can do this comparison pairwise. You know what I want to do next? I want to map this to a pairwise problem. What we can do is we try to group all these species, okay? So this problem was converted eventually to a binary programming issue, which was this is a well-solved problem in discrete mathematics, integer programming. Okay, so if you look at this xi is each value is either 0 or 1 for a species. So if it's 0, that means this guy belongs to a group, and it's not a group leader. Okay. If it's 0, if it's 1, that means this guy belongs to a group and it represents a group. So each group you just need to take one guy to do the representation. So what you do here, you just take the sigma. This one you want to minimize the number of groups. How many groups you can have to mimic everybody. This is target function. This is the constraints. Okay, constraints means xi either is 0 or 1. So this one is rather straightforward. This equation tells you each species at least must be represented by one guy. This is a constraint. So you just solve this binary, this integer programming issue. Then you can find the minimum number of groups to represent them. So you just don't need to pay too much attention to the detailed math. You can go back to take time to look into it. But the idea here is still, if you want to solve a combustion problem, if you can transform this equations to something else that has already been well solved, it can save you a lot of trouble, and also it can make the solution much easier and trustable. Okay, so this is how we can find the minimum number of groups for diffusion. What we did, we tried for ethylene and we tried for n-heptane. For ethylene, this is the threshold, how much error you can tolerate, and this is how many groups eventually you will end up. So if we can tolerate 10 groups for ethylene, if we can tolerate 10% error, eventually you will get 9 groups for ethylene. Similar for other small molecules, you got about 9, 10 groups, that's it. For large engine fuels, n-heptane, for example, we find less than 20 groups are sufficient. So rather than solving 500 by 500 diffusivity groups, you just solve 20 by 20, that's it. If you can work on reduced models, what do we find? 15 groups are more than enough for real jet fuels, for dodecane, whatever. So therefore, with 15 species, you can 15 groups, 15 diffusion groups, you can pretty much take care of all the fuels. So diffusion, eventually, you can get rid of the cost. So 15 by 15, that's nothing already, right? So eventually, if you look at these reduced models are the 9 group for ethylene. So basically, the lines are without lumping. These symbols are with lumping. So different pressures for premise flame and the flame structure. You can see this reduction give you very little error because error is controlled. Again, the worst case error is controlled to be smaller than 10%. But on average, you don't find 10% error everywhere. So most other places you find perfect agreement, but the worst case error is 10%. Okay. This one we can further reduce this model. So my student just recently he did further reduction. He simplified. Let me just show you the result. Eventually, he simplified to 3 groups versus 15 groups. He can even reduce it, but he just likes to do it. It's good. But 15 by 15 is not a big deal already. But 3 by 15, it's really cheap. It's linear function, and it's constant already, right? So that means theoretically, if you can use a few Lewis number, probably you can also deal with turbulent flames. Not a one Lewis number. If you can use 3 for different Lewis number, 3 Lewis number, let's see, because you use 1 Lewis number for this, 1 Lewis number for this, 1 Lewis number for this. You can probably take care of very big models. Not a 1 Lewis number, 3 can be very accurate already. That's a story for diffusion, okay? But the story here is diffusion doesn't take much time. So the last part left is the development of solvers. It seems to be a lot of mathematics in this solver development, but actually it's straightforward. We can quickly go through these slides because we went through all the background already. We spent hours yesterday to talk about the ideas here, okay? For chemistry solver, the key issue is the stiffness. And we set a short time scale, very, very short time scale for radical give you the problem. In most cases, you need to deal with this with implicit solvers. When you have an implicit solver, Chemicon 2, you use numerical perturbation to evaluate the Jacobian, and use dense matrix to do LU factorization. So that'll give you the most time-consuming part, okay? Because chemistry is time-consuming, so in old days, people, when they solve 3D field, they tend to use splitting scheme. Then we mentioned why we want to use splitting scheme. Because if you don't split it, you need to solve the whole flow field, like millions or billions of variables together with a huge matrix. There's no way you can do Jacobian for this big matrix, okay? After the splitting, you can deal with chemistry locally. So let's say you get 30 species, you can do 30 by 30 Jacobian locally. But the diffusion and transport part, you can do some iterations, or even you can do explicit integration. So therefore, let's look at this. Splitting scheme, basically, this is after discretization. So this is a vector of dependent variables. This is a chemical source term, this is a transport term, okay? Splitting means you can approximate this real system this diffusive reactive system with two different ones. The first ODE is you only have a chemical source term. The second one, you only have a transport. So you do this for half step, you do this for one step, you do this for half step, then you hope the result is the same. Just like the analogy I gave you yesterday. If you have two people giving me money, so you give me $5, you give me $5, I can collect you first, collect $5 from you next, right? Put together is $5. But again, chemistry is not that straightforward. So chemistry means you guys are smart, right? You look at how much you give me, and you can decide on the fly how much money you want to give to me. So if you see I collect $5 from her, and you probably give me $10 because you want to give me more, right? Or sometimes if you see, so the lesson here is if you get a coupled process, and if you separate them, you can get a totally different result. Another analogy is if you want to see a game, for example, you get two teams play each other. You know, there's people have very complicated response. If you get two guys fighting each other, you put them together, you have a game to watch, right? You got all different moves, okay? But what if you do splitting? You put the first guy to a cage, right? 5 seconds, take him out, put the second to the cage, and then you do this over. You think you see the game? No, that's not the case. So for the same reason, you don't expect splitting scheme always work. We can show you when it doesn't work, when you have the strong coupling. Okay, let me give you an example. This is an example when it will fail. So people have been noticing sometimes splitting scheme fails, but we just didn't find a systematic scenario. It always fails. But this one tells you when it always fails. So when you see similar problem, never try to use splitting scheme. Okay, that's forced ignition problem or extinction problem. If you try to capture extinction behavior or forced ignition behavior, the chances that you cannot use splitting scheme. So here's the example. For example, you have a simple reaction. Fuel go to radical. Radical go to some intermediate. Okay, and this radical, let's say it's H. It serves as a catalyst for fuel go to final product. This is two-step mimics what happens in real chemistry, right? Radical formation through a quasi-steady-state approximation. R forms slow and quickly decompose. Quickly goes away. And then the concentration of R determines how fast overall oxidation goes on. Like each radical pull concentration changes the overall reaction rate. Okay, if you have the reactor have some external source of a radical, for example, in a flame, if your neighbor has a lot of H radical, it gives you a lot of H from diffusion. So what we can do is we put a diffusion source term to this process to see whether the system can be predicted by splitting. Okay, so let's take a look. How about this? Let's just skip this. I can tell you why this fails, because if you look at this R, R's consumption rate is very fast, right? You can reasonably assume R is in quasi-steady state. Okay, its consumption rate should be equal to whatever forms R. Okay, so how many formation paths do you have? This is one formation path. This is another one. So therefore, this consumption rate should be equal to this formation rate, diffusion rate plus the chemical formation rate. Or in another word, R concentration should be equal to the formation from A plus diffusion divided by the large rate parameter, right? But if you do splitting, what will happen? If you do splitting, R is still in a quasi-steady state concentration. Its concentration would be in a splitting scheme. The transport is gone in the chemistry substep. So R concentration would be equal to chemical formation rate divided by its large consumption rate. So it will be totally wrong. So this will be correct one, this will be wrong one. You can change this number to make this error arbitrarily large or even totally off chart. Okay, so therefore if you split the guy, the radical pool can be messed up. The consequence will be like this. So here we use this to do a real splitting scheme. The The actual simulation result should be like this. A concentration should be like this. B concentration should be like this. If you do splitting, you do stress splitting, you find the actual solution will be like this. The fuel and the product will be totally wrong. The error is factor of 2. It's way beyond the numerical error. That's the splitting error. People call it splitting error. And how can you suppress the splitting error? You have to reduce your time step. Let me just show you how small you need. Let me just quickly go here. You know this stress splitting for this toy problem, right? This tells you how much error you will have in the product. So basically, you see the time step range for this is normalized problem. So from here, you should already get quite a reasonable agreement. But if we keep on reducing the time step, even to this regime, the error is still quite large. So this is a plateau here. So that means you have to reduce your time step to somewhere, you see, it starts to fall. This regime, do you know what this time step is? This time step is comparable to the time scale of R, the radical time scale. So that means you have to reduce your time step till the problem is no longer stiff. So why that will work? Because in that case, people don't have the time to look at each other. You can do splitting there. So when the two, this time step, when the two guys are decoupled, then you can do the splitting. If they are coupled, you cannot do it. Okay, but then it loses our purpose for using splitting is to use large steps to take care of the stiff problem. If your time step has to be close to the time scale of radical, then what's the point to use splitting? So you have to take care of this, right? So how can we take care of this? Now the solution is not to do splitting because you are dealing with different systems. So let's look how do we handle this issue if we don't do splitting. So the whole point here is that we found one of the solution is to do hybrid. The hybrid is we are assuming the transport problem, diffusion or convection, give you less stiffness compared with chemistry. So chemistry gives you much shorter time scale compared with the other two source terms. For convection, what time scale do you have? If you get a compressible flow, that's called a CFL condition, right? So your grid size divided by acoustic speed, sound speed, that will give you the convection time. Make sense? But if you are dealing with incompressible flow, the convection time would be grid size divided by the flow velocity. So it differs by approximate order of magnitude. So whether 300 meters per second or 30 meters per second. So that's why for compressible flow, you typically need to take smaller time step if the CFL conditions are limiting it. Diffusion time depends on the grid size. So grid size squared divided by diffusivity, or D. So basically, delta squared over D. This one gives you the diffusion time scale. So unless you use tiny small grid points, then diffusion typically is not stiff to you. Okay, as again, delta over some kind of velocity, relevant velocity, give you convection time scale. So if you use RAS LES, your grid size is large. Typically, you can almost treat diffusion and convection as non-stiff. Just use sufficient small time step. So diffusion and convection is non-stiff. Then you can take care of these two terms explicitly. But chemistry is still stiff. Suppose you use 10 to the negative 7 second time step. Chemistry is still stiff, right? How to deal with stiff chemistry? What we did is we look at a governing equation. For example, this is a chemical source term. This is let me just go back to previous one. If you look at this equation, this is a chemical source term. This is transport, diffusion, the convection term, right? We know this term is stiff. What? Yeah, sorry, just give me 1 second. All right. So the key point here is if something is slow, why do we bother to include the slow process in the implicit core to solve, right? We only include those stiff terms, fast species and fast reactions in the implicit solver core. Everything else we do explicit. So there's typically only a small number of species and reactions which are faster in whatever small time step we take. So therefore, if we do this, we can include in this discretized equation. Let me just get rid of this. So the red color shows fast species, okay, and everything else are slow. The slow species we show in dark color, and also slow reaction and a slow transport process, we all group them together. So this is a non-stiff source term. These are stiff variables. These are non-stiff variables. We can decompose the ODs to this two parts, fast and slow parts. Okay, for this part of fast species concentrations, we do need to solve this equation implicitly. All right, and for this whole part, we don't have to do implicit. We can do explicit equation. So that's the whole thing. We solve the whole equation together, but fast variables implicitly, everything else explicitly. It turned out this method works quite well, and even faster than splitting scheme. If you look at this, so basically, first of all, the splitting error is gone using this approach, the hybrid approach, because we solve transport together with the chemistry. By solving these two together, there's no more splitting error. Okay, these two always coupled together, and also, so the time step you can take. If you can take a shorter time step, you can get a better error. So this slope tells you the order of accuracy. Okay, so this one tells you the first order accuracy, because in the previous scheme I told you the discretization was giving you first order accuracy. Okay, you can also possibly design a second order accuracy. We have other schemes we can use to improve the order accuracy. If you see you do need second order accuracy, you can use a little bit more complicated formula to do it. Okay. And this one shows you in real problem. I showed you a bad example for splitting scheme for a toy problem. This one I show you some forced ignition case for real hydrogen system. So in hydrogen air, so this is stir reactor. In stir reactor, what we do is initially the stir reactor doesn't have flame in it, but we have a lot of radical input at the inlet. We put a lot of H radical to force the reactor to ignite. So this forced ignition, if you use splitting versus non-splitting scheme, the line gives you the correct solution from full system. And adaptive scheme gives you a correct solution like this. So the solution is right. Okay, splitting scheme will give you a wrong ignition delay time for the stir reactor. So for example, if you get a lifted flame or jetting cross flow flame, this is very similar. This can be a similar issue if you have some radical source somewhere. Okay, but for this case, you get a factor of 2 error in the so-called ignition delay time. Then when we show this, people argue, oh, this is an extreme case, so probably we don't have that strong H forcing. But if you look at H concentration, you get a lot of H input. So for example, you get a lot of H input and this to force ignite it. Probably we don't have this H input at the real combustor. That's reasonable. We don't have, how do you put H at the inlet, right? It's not very real. So how about let's look at something else, extinction problem. Extinction is so relevant to a lot of flames. Turbulent flame, flame blowout, a lot of, what if you want to predict extinction? Limb blowout, okay? So this is what happens if we have a stir reactor running. Stir reactor is running, and then if you want to predict what happens, if you increase the flow rate a little bit, it will try to quench, to extinguish, right? So this is what happens. So from the upper branch, we keep on increasing the flow rate. This is S-curve upper branch. It goes down until it approaches the turning point. And then you see, so one guy extinguishes, the other guy is surviving. This is a real flame. In real flame, because in the splitting, you still have the H radical in the reactor. So it survives. It can survive there for much longer time. But with splitting, it just dies. And this difference in time scale, you can look at it as order of magnitude. So your extinction time is totally messed up. So if you want to predict lane blowout issues, for example, whatever sense relevant to flame extinction, the chances, we tried many different cases. Almost for every single case, you will find order 1 large error for extinction prediction. So the reason was what happens, as we explained, for the force ignition. If you mess up the radical pool, you messed up the chemistry. That's it. And there's no easy way to fix the radical pool because it's nonlinear issue. If you want to correct it, how do you correct the radical pool size? Okay, so this is the lesson we learned. And then what we can do is if we want to add other component to our solver, we don't split chemistry versus transport. And remember, we can use analytical Jacobian to improve the simulation result, right? And also we can use sparse matrix operation. So this is like an example for sparse matrix, how sparse it is for USA Mag 2 Mag. So if we formulate the problem right, the Jacobians look like this, very sparse. If you use sparse Jacobian operation, the time cost is like this, okay? And the dense matrix looks like this. It's a cubic function. Sparse matrix like this. Keep in mind, this is in log scale, and each of this is 2 orders of magnitude. You see, this is 4 or 5 orders of magnitude for large matrices. Okay, so deal with large matrix. Make sure you use sparse matrix operation. You download it from anywhere on the website. It can save you a lot of time. You don't have to wait there just for many days for the result. And what if we put an analytic Jacobian, sparse matrix, and all the hybrid, whatever, all the technique together? So the best we can do so far is this line is if we don't do anything, use ChemCam 2, the original ChemCam 2 model, give you this line. This is what we measure for the different mechanisms, number of species, basically, how many species you have, 1, 2, 3 different cases. This line, the bottom line, is how much time it takes for each rate evaluation. So that's pretty much the bottom line you can do, the best you can do for any solver, because at least for each time step, you need to compute 1 reaction rate, right? So this is minimum you can do for any solver. So if you only use analytic Jacobian, you find it's this one. Analytic Jacobian, it helps a lot for small mechanisms. And for sparse matrix, if you put together, it gives you this line. This line is analytic Jacobian together with sparse matrix. It gives you much faster solver, but together you can get this trend. This trend is comparable to this trend, right? So this is linear scaling, and this is linear scaling. So the cost, if you use analytic Jacobian together with sparse matrix, your computation time will become a linear function as number of species. So that means if you can use 100 species in your simulation, you can also use 200 species. Just spend twice the time. That's not a big deal, right? But in old days, if you multiply your number of species twice, you need to spend almost an order of magnitude more time to compute it. That's why people keep on asking me for 15 species. I said, I have 30 now. Why don't you use 30? You just use twice the time. And why you want to use 15 species just to mess up all the accuracy? But they don't want to change the code. That's it. Okay. So if you put sparse Jacobian, analytic Jacobian together with adaptive, just hybrid, this hybrid issue, partially explicit, partially implicit, it goes here. So basically, this is what you can. This one, this red circle, is what you can do. So this is so far the best thing we can do for implicit solver. We lower it down to almost a minimum level, just to make a comparison. You know, this rate evaluation is our optimized rate evaluation. If you download the reduced models from a website, your computational time is here for rate evaluation. But if you call the ChemCam subroutine, CKLib, like a CKWIP in ChemCam package, the cost is here, this open down triangle. So if you look at our cost for implicit solver, it's almost the same as what you will do for a single rate evaluation using ChemCam 2 for rate evaluation. Okay, so this is dramatic. Basically, this tells you the implicit solver is already very efficient. if you can try all these techniques. And the accuracy is very good. So there's no need to split the equation anymore. Okay, if you want to predict flame blowout or whatever, and this is a further check we did for the jet fuels. We got to reduce the amount of jet fuels we just showed you before, and this is how much if we use Chemical 2 to compute it. And this is a single rate evaluation optimized, and this is how much time our just fully optimized solver. So analytic Jacobian plus sparse LU plus hybrid, it give you this line, this red circles. That's it. So it can save you a lot of time. And eventually, did I have, okay. So this is the last slide I want to show you guys. So it's a tough 6 hours, okay? It's a Thursday, Friday afternoon. Thank you very much, you guys, to still sitting here, listen to me, going through all these equations, whatever. I hope you do have some message to bring home. But here are the most important message I want to mention here. So first of all, just pay attention to the sampling issue. Where do you sample the reaction states? It's very, very important, and people didn't pay enough attention to this before. If you sample from the wrong reactors, you probably will have large errors in your simulation. And we found sampling from auto-ignition plus stir reactor can give you very good result. Actually, that's the good news, okay? You don't have to include a lot of complicated flame simulation. That can save us a lot of time. And then error control is critical for model reduction method. If you want to reduce good reduction method, make sure you can control the worst case error, because otherwise you need to do post-validation. It boils down to a sensitivity analysis issue. You need to spend a lot more time to figure out what threshold you want to use. Okay, error control is critical. HiChem, I can emphasize more on HiChem. If you guys want to go back to try, we will have a HiChem model, reduced model available very soon. You can give it a try to see how it works for you can do your simulation to compare with the experiment for real fuels to see how it works. It's very exciting. And tuning is critical. So when you try to tune complicated models, so try to avoid overfitting. I don't try to just report people the targets you tune against, because with complicated model, it makes no sense only to show people what you tune against. You can always get good results against those targets, okay? And for the solvers, just remember several things. So analytic Jacobian, if you need analytic Jacobian, you can send me email, by the way. I can generate analytic Jacobian for you for free. If you need to use it, speed up your simulation, I'll just give it to you. Typically in your solver, if you use VOD or whatever solver, there's just a single switch. You just need to change it from one number to another number. It will call the Jacobian automatically. So there is very little change in code is needed if you want to use analytic Jacobian rather than numerical perturbations. So you change it, spend 5 minutes to change your code, it can save you weeks in simulation time, okay? Sparse LU is a little bit more complicated in terms of programming. You need to find sparse linear algebra subroutine from online. So you need to integrate those sparse LU into your code. But it can save you a lot of time for large models. If you guys work on detailed chemistry, if you are just not patient waiting for the second simulations, just make your sparse version. That will just make it blinking fast, okay? And then try not to do splitting if you are dealing with extinction problems, okay? Forced ignition, extinction are similar issues. So if you want to predict flame blowout, you want to flame holding, these kind of issues, sometimes even strongly burning terminal flames, it's very risky to use splitting error. So you can't guarantee your solution will be right or even close. Okay. All right, thank you very much, guys. You have a wonderful trip back. Okay.